Dear students, we are in the lecture of structural analysis part 2. Flexibility method is the unit we are seeing. We have seen the flexibility method. We have analyzed it for simply supported continuous beam, and for one end fixed and another end hinge condition. We have also seen the sinking of the support criteria. Now in this lecture we'll see the flexibility method, and we'll analyze a portal frame. Okay, there is a portal frame in our syllabus also, and uh, let's start with this. Analyze the frame by flexibility method and draw shear force and bending moment diagram. So this portal frame is given having spans AC and CD. AC span is a 4 meter span and CD span is 3 meter span. AC column is having a point load of 50 kilonewton exactly at the center and is having EI as 2I. Okay, sorry, E will be the same for all the cases, that is it is 2 into 10 raised to 5 Newton per mm square. And what the moment of inertia factor I value is for AC span, it is 2I. Okay, and for CD span it is only I, that is 1I. Okay, and CD span is having a UDL of 25 kilonewton per meter for a span of 3 meter. Okay, now keeping all the keeping all the analysis steps similar. Okay, there is not any type of difference in the steps for the portal frame. Okay, so the first step is finding out the degree of static indeterminacy. So totally we have here three unknowns, sorry, these three unknowns, that is one is movement, one and another one is horizontal horizontal load, and third one is vertical load. Three unknowns for the fixed end, and for hinge end it is having two unknowns. So 3 plus 2 total 5 unknowns are there, and we have total 3 equilibrium equations. So 5 minus 3 gives us the 2 redundants. Okay, 2 unknowns are there and we have to analyze for these 2 redundants. Okay, so we'll select the redundants. So we select the redundant at this place. Okay, so vertical reaction and horizontal reaction. So we'll consider VD, that is vertical reaction at D, as the first redundant, and then horizontal reaction at D, HD, as the second redundant. Okay, for our convenience, okay, you can select redundants from here also. Okay, and most important thing, if you consider movement as the redundant, then we have to calculate the theta value, the rotation value. Okay, so it will go in much deeper case. We'll see that type of numerical also, but for this case we'll go for the redundant reactions. Okay, reactions at D point. You can take reaction at this A support also. Okay, it is as per your choice, there will not be any change if you take such a type of redundants. But why I am taking redundants at D point? Because if I consider redundants at this hinge end, then this beam CD will behave as a cantilever. Okay, so obviously analysis of cantilever beam is much more easier than other type of analysis. That's why only. Okay, then we'll go for a release structure diagram, and we'll remove the redundants. Okay, now here this is the first given diagram. This diagram I have removed that redundants. Okay, so it is acting as cantilever beam. Now here we have shown in M1 diagram, we have shown first redundant we have considered VD, vertical reaction at D and will show with the amount of unit load, that is Vd is equals to 1 kilonewton. Okay, the second redundant we have considered Hd, okay, and is equals to 1 kilonewton. This is M2 diagram. Okay, this is M diagram, this is M diagram, this is M1 diagram, and this is M2 diagram. Okay, these three diagrams are very much important, and accordingly we'll prepare that table. Okay, this table. Now what we have done in this table, we have divided into this table into members, origin, M. This M is the movement diagram, actual loading diagram. M1 diagram is for redundant 1 diagram, M2 diagram is for redundant 2 diagram, and limits. Okay, now what we have to do for this M diagram, we are going to simply cut the sections. Okay, now our this portal frame is divided into 3 spans. First one is CD span, second one is CB span. If there is any change in load or change in moment of inertia, okay, if any change in the section or the characteristics of the beam, then we'll consider that span separately. Okay, so we'll consider CB separately and then B to A separately. Okay, so we have three members, DC, CB and BA. Okay, now we'll consider first member CD, and for calculation of movement we'll cut one part here. Okay, and we'll take the moment from this free end. Okay, so what will be the quantification of movement, and obviously as this load is going downwards, it will create this type of movement, clockwise movement, and clockwise movement we have considered positive, sorry, clockwise movement we are considered negative, anti-clockwise we are considering positive, or you can take vice versa as per your choice. Okay, so minus 25, this distance will be x, so minus 25 x into x by 2, that is minus 12.5 x square. Okay, then moving for this C to B span, C to B span does not have any load up to, okay, but it we have to consider all the loads, all the loads movements coming in our way. So we'll consider 25 into 3 square by 2. Okay, and as this CB span doesn't have any load, we'll keep it blank. Then for this BA span, we'll cut a section here likewise. This distance will be x. Now we consider all the loads coming from D point. Okay, so 25 into 3 square by 2 and minus 50 into x. Okay, this point load into x. Okay, this is for M diagram. Now moving towards the M1 diagram, this diagram, M1 diagram. So again we'll cut the sections likewise. Okay, here we have VD load, that is unit load, but what we have considered, what we do here, just a minute, we will consider this one VD, that is 1 kilonewton into x, so this distance will be x, so minus x will be the moment at the B to D span. Now moving towards the CB span, okay, so here we'll cut the section. So what will be the quantification of movement? So it is 1 into 3. Okay, the loading value is known 1 and distance is known 3. Okay, that is minus 1 into 3, and here it doesn't have any load up to this part, so we'll keep minus 3 as the M1 diagram for CB. Okay, minus 3 will be the moment due to redundant 1. Then for CB diagram also it is minus 3 only, same, right? Then moving towards the M2 diagram, that is movement diagram due to redundant 2. Now as you can see here, this distance is x. We take movement as a load into perpendicular distance. So load is actually horizontal and distance is also horizontal. So for this BD span it will not count. Okay, so HD movement, HD load value will not count because we have horizontal load and horizontal distance. Okay, so load into perpendicular distance is the movement. Okay, that's why we will not consider for this BD span. Okay, we cannot consider because distance is 0 and the load is going through the BD member BD, that's why. Then for C to B span, we consider it as a 1 into x. Okay, so this one load, one horizontal load, and this distance is vertical. So now we can consider plus x, and for this BS part we consider we'll consider x plus 2. Okay, x plus 2. Now what are the limits? Limits for DC span it is 0 to 3, for CB span it is 0 to 2, and for BS span it is 0 to 2. So these are the limits value. Okay, now we will go for the coefficients calculation. So displacement at redundant, so it is the multiplication and integration of original or loading movement diagram into M1 diagram. Okay, so likewise we will get the dr1, it is the displacement at the redundant 1. dr2 it is m into m2, just remember these 2 points. So redundant 2 is m into m2 and it is displacement at second redundant. Okay, now we go for flexibility coefficients. F11 is m1 into m2, sorry, m1 into m1 also. Okay, m1 into m1 only. Okay, that's why we have done square of all these movements. Okay, m1 into m1, that is m1 square. So we will get this F11 coefficient. Then F12 and F21 is m1 into m2 between integration of limits 0 to L. So we will multiply with m1 and m2. So we will get this F12 and F21 coefficient, and this F22 coefficient is m2 into m2. So m2 square, that's why we have done square over here. So we will go get all the 4 coefficients. Why we get the 4 coefficient, not 6 or 8? Because we have 2 redundant values, and because of that 2 redundants will form a square matrix. Okay, 2 by 2 square matrix, that's why. If we have 3 unknowns, then we'll go for a 3 by 3 square matrix. Okay, now we doesn't have given any sinking of the support or displacement value. Okay, that's why we'll keep total displacement in the indeterminate structure is 0 in the redundant 1 and in redundant 2. Okay, it is 0. Then we go for the compatibility equation. So this is the compatibility equation. What does it exactly means? It is di is the displacement in the indeterminate structure is equals to dr is the displacement in the release structure. So what we have calculated here is displacement in the release structure, these values. Then f is the flexibility coefficients that we have calculated here, and into r is the number of, sorry, r is the redundants, r1 and r2 are the unknown values. Then we'll calculate, and likewise, and accordingly we will get the value of R1, that is vertical displacement at D is equals to 44.9 kilonewton, and R2, that is horizontal displacement at D, as 103.33 kilonewton. So these two are the unknowns that we are getting. Now the next and last part is to draw the shear force and the bending moment diagram. So we will complete the numerical likewise. Okay, so as you see, there is no any change in the analysis of the portal frame. It is same as in case of the analysis of beam, but in the first step over here, in the degree of static indeterminacy, for beam case we have neglected axial force. Okay, but we cannot neglect in the portal frames or columns. Okay, so we have to consider here that axial force also. Okay, if you have any doubts regarding this, then you can directly contact me. Thank you.